As a podcaster, I discovered that there are guests for which the hardest is to know when to stop the conversation. They could talk for hours, and that would make for at least 10 fantastic episodes. Frank Harrell is one of those guests. To me, our conversation was both fascinating, thanks to Frank's expertise and the width and depth of topics we touched on, and frustrating. I still had a gazillion questions for him. But rest assured, we talked about intent to treat and randomization, proportional odds, clinical trial design, biostats in COVID-19, and even which mistakes you should do to learn Bayestats. Yes, you heard right. Which mistakes? Anyway, I can't tell you everything here. You'll just have to listen to the episode. A long-time Bayesian, Frank is a professor of biostatistics in the School of Medicine at Vanderbilt University. His numerous research interests include predictive models and model validation, Bayesian clinical trial design and Bayesian models, drug development, and clinical research. He holds a PhD in biostatistics from the University of North Carolina and did his bachelor in mathematics at the University of Alabama in Birmingham. This is Learning Bayesian Statistics, episode 45, recorded June 17, 2021. Welcome to Learning Bayesian Statistics, a fortnightly podcast on Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country, and reach a true Bayesian state of mind by visiting learnbayesstats.com. That's learnbayesstats.com. Do you want to support the podcast and unlock exclusive Bayesian swag at the same time? Then you can visit my Patreon page at patreon.com/learnbayesstats. Starting at €3, you can get various benefits like the private MBS Slack channel, early access to special episodes, selecting questions for episodes, or even coming on the show. You'll get more details at patreon.com/learnbayesstats. Thanks a lot, folks. I'm very grateful for any support you can bring me.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations.
What's a Bayesian? Is someone who cares about evidence and doesn't jump to assumptions based on intuitions and prejudice. A Bayesian makes predictions on the best available info and adjusts the probability, cause every belief is provisional. And when I kick a flow, mostly I'm watching eyes widen, maybe cause my likeness lowers expectations of tight rhyming. How would I know unless I'm rhyming in front of a bunch of blind men dropping placebo-controlled science like I'm Richard Feynman?
Frank Harrell, welcome to Learning Bayesian Statistics.
Alex, thank you for having me.
Yeah, well, thanks for taking the time. It's always a pleasure to talk about the fascinating field of biostatistics that I guess a lot of people have heard about in the last year. And by the way, you must have been really busy in the past year.
The busiest of any time in my whole career.
Well, I think that's probably good news for us. But before we dive into what you're doing, by the way, let's start with your background, because you started with mathematics and then shifted to biostats. So I'm curious, how did that happen and what's your story, basically?
Yeah, it was really amazing how things unfolded. A lot of dumb luck was involved. So I always loved math. And then I had a part-time job in a medical center in Birmingham, Alabama, University of Alabama, and got to be involved in analyzing data. I always liked numbers, and so I found out I really liked analyzing data. And then I was lucky enough to meet the chair of biostatistics at University of Alabama, Birmingham, David Hurst. And he sort of took me under his wing, and I started... As an undergraduate, I started taking some graduate biostat courses, but I still wanted to go into pure math. And so Dave took me in his office and had a little sit down, and he said, math is a wonderful field, but let me tell you about the job market in biostatistics. It's just a little bit better than the job market in math. And he told me in graphic detail how much better it was. And he said, what you need to do is to go to University of North Carolina, get a PhD in biostatistics with a supporting program in computer science and in biomedical engineering. I did almost exactly what he said, except my supporting program was really physiology and biomedical engineering. He was way ahead of his time, and his advice was some of the best advice I'd ever gotten. So he got me into biostat and kept me from going to graduate school into pure math. I still love math, but the ability to use math for tackling very concrete problems with data is really a fun thing for me.
I completely agree with that. But I'm pretty amazed by the quality of the advice.
It was amazing.
Yeah, you got. I mean, especially like it was a few years ago, and so I mean, computer science, I'm guessing, was not as important as it is right now, and computers were much less powerful. So having this insight of, okay, you need a computer science major, or I don't know how you call that. That's pretty amazing to me. You were pretty lucky.
More
there.
than lucky.
Yeah, but you followed the advice. That's what interesting to me. Like, had you already heard about biostats, or like was it completely new to you when he gave you this advice?
No, I had already taken some courses, and I was already helping a lab analyzing their data. So it's not like I was foreign to it. It's kind of amazing. I still wanted to go into pure math until he took me into his office. But yes, I was already lucky to be exposed to biostat, and I was lucky that several biostatisticians in his department gave me some of their time to give me advice about data. And so I was doing things I had no training to do, but I was overextending myself, but getting great support. So I was lucky to have quite a bit of exposure.
Yeah, I mean, that sounds like a lot of fun. And actually, well, what do you do today? Like, how would you define what you're doing nowadays? Because you work on a lot of different topics, and also, of course, how does that relate to Bayesian statistics? I mean, how useful are they in your field?
Yeah, and so there's so many things you can work on as a biostatistician, and that's a real plus. The variety is endless. And so I do a lot of work in developing predictive models and model validation and dealing with data complexity such as missing data. That's not using Bayesian methods directly most of the time because we're very empirical about our modeling. We use some Bayesian ideas in terms of getting prior information about the structure of the models. There's statistical modeling, and then there is a lot that we do to help investigators optimize measurements. This is something that most biostatisticians do not get themselves involved in. They take the measurements for granted and assume that they have reliability and that they have sensitivity to the underlying process. And we find that in most studies, the measurements have a problem, and the statisticians have to get in and work hand in hand with the investigators to improve how disease is measured, how patient outcomes are measured. And then there's design. So design of studies is quite a bit different from analysis, but of course it has to be related to the analysis because you design it to be able to estimate certain parameters. So you need a model for the parameters you're going to estimate. And so the design work also involves a lot of work about outcome measures and how often do you measure outcomes? How do you deal with longitudinal data? And so I've always been a modeler. And so I think of design from a modeler standpoint that I want the design to be causal. So I want the design to involve intent to treat and randomization. And once you have intent to treat and randomization, the models sort of automatically become causal. And the question is, how do you have a model that is true to the data generating process? And so that really involves handling baseline variables optimally. How do you take into account that patients who get COVID who are older have a higher mortality than those that are younger? A lot of people publish analyses where they don't distinguish the young from the old. And you can think about what a tragedy that is in COVID because age is such a dominating predictor. But it's amazing how many studies don't believe in covariate adjustment. They don't take those heterogeneities into account. So how do you model age and how do you not assume it's linear? So we do a lot with flexible modeling. And then the other thing that's really come into play during COVID, it's always been a big field, but it's bigger now, which is longitudinal analysis, because most of the outcomes in COVID are measured daily. And so we have daily longitudinal data, usually measured over a month or more. And so how do you make optimum use of longitudinal data? And that's where Bayesian methods play a large role, because a lot of the longitudinal methods, we don't have exact solutions for that except with Bayes. So frequentist, we have a lot of approximate solutions, such as using random effects models and large sample theory with other kinds of longitudinal models, but with Bayes, you get exact models, exact inference, and it's very, very flexible. The other way that Bayes comes in is relaxing the model assumption. So one of the models that's central to our work is the proportional odds model, because it handles an ordinal outcome, and a lot of the COVID outcomes in COVID treatment studies are ordinal. And then what if you don't want to assume proportionality, or you don't want to assume that the treatment has the same effect on symptoms as it has on mortality? So you can partially uncouple the effect of treatment on one outcome versus another using models like the partial proportional odds model, which a former PhD student of mine created, Brasidas Peterson, back in 1990. And so we have a Bayesian partial proportional odds model where you can put a prior distribution on the departure from proportional odds. So you can borrow information, which Bayes is great at doing, and you're borrowing information about symptom relief in how you analyze mortality, but you don't have to trust that the treatment affects those two outcomes exactly the same. So the Bayesian approach allows you to have complexities in the model that are sort of half in the model and half out of the model, because you might have a skeptical prior distribution on the complexity, such as the non-proportionality.
Okay, well, fascinating answer. I have a lot of follow-up questions. So we're already going off script there. Longitudinal data, it's when you follow the same patients, right, throughout time. Okay, that's why you were saying that's very important for COVID. Second question is the proportional odds. Maybe can you detail that a bit more? What's this kind of model, and why is it called even proportional odds? I think that would be interesting to listeners, because we didn't talk about these kind of models yet in the podcast.
And these models are not taught nearly enough in graduate school. And so it's very akin to the proportional hazards model for time to event analysis. And the proportional hazards assumption states that the effect of a treatment or a baseline variable is the same no matter how far along you get in the follow-up. So you take everybody still alive at 1 year, what's their risk factors for dying now? Take everybody who's still alive at 3 years, what's their risk factors for dying now? So it assumes that the magnitude of the increase in instantaneous risk is the same over time. So that's the proportional hazards assumption. And in the proportional odds model, you don't have time, but you have the severity of the outcome at a single time. And so the outcome may go from coughing and sneezing all the way to fever, to respiratory failure, to death. And so the assumption there is that the treatment and other variables affect going from, say, level 1 and higher in the outcome scale the same way they affect going level 2 or higher, or 3 or higher. So it's like proportional hazards in time, the time effect, except now we have the severity of outcome effect being proportional. You can reduce, when that assumption is true, you can reduce your treatment effect to a single odds ratio. The wonderful thing about these models is they generalize the Wilcoxon test. And just about everybody's familiar with the Wilcoxon test, which is asking whether the outcomes in treatment B tend to be higher than the outcomes in treatment A. It's a ranking method. And so the proportional odds model is one of the class of semi-parametric models that just uses the ordering of the outcome, and it doesn't use the spacing of the outcome. And that's what makes it so wonderful. So it doesn't assume that going from no symptoms to coughing and sneezing is the same as going from coughing and sneezing to dying. So the spacing between those categories is arbitrary and not assumed to be anything particular. So we often call the categories like 0, 1, 2, 3, but it would be better to think of them as A, B, C, D. So you're modeling something like A, B, C, D.
Okay. And so it's saying that it can be harder to go from B to C than to A to B. That's what you're saying?
Yes, it can mean different things. It can mean worse things. There's structure of similarity in how you move across the categories, but the actual meaning of the categories can be very non-constant in how you interpret those increments.
Okay. I think I see what you mean. That sounds super interesting. Do you have some resources for listeners who are interested to dig deeper that we could put in the show notes?
Yeah, we have a website that has all of our work in the last year and a half, which is hbiostat.org/PROJ for project/COVID-19, one word. And that has a lot of material about ordinal models in general, especially at the bottom of that page. And it has a lot of material about ordinal longitudinal models and about the proportional odds assumption, the relationship to the Wilcoxon test and the Kruskal-Wallis test. It's got a ton of material on that page and a lot of code and a lot of examples worked out.
Perfect. That's perfect. It's already in the show notes then. And yeah, I'm sure I encourage people to go there if they want to dig deeper. I know I will. That sounds super interesting. And actually, weirdly, I'm doing quite a lot of electoral forecasting, and I can see similarities in how you would model choice of people. Like especially in France, when we have a lot of different parties and people go from one party to another kind of in an ordinal manner. Like you don't really go from like your probability to, if you tend to vote to prefer the far left party, your probability to switch to the left party is much higher than the one of switching to the right party.
And the other thing about ordinal models is we're using them for continuous outcomes where most people would use a linear model. I don't actually use linear models hardly at all anymore because the semi-parametric models are invariant to how you transform the dependent variable. So if you think you should take the logarithm of some financial figure, some cost, you're doing an economic analysis. If you think you should take log, but you're not sure, maybe it should be square root or maybe it should be the original scale. Well, in the semi-parametric models, like ordinal models, it doesn't matter how you transform the dependent variable. And it also handles strange distributions like bimodal distributions or floor or ceiling effects. So you can handle things that are mainly continuous, but they may have a discontinuity somewhere. So the variety of things they can handle is pretty amazing.
Okay. But then I think for elections that doesn't work then, is you don't have continuous results, unfortunately.
Right. But if you're predicting, some continuous thing like amount of money something costs or whatever, it'd be more pertinent there.
Yeah, exactly. Yeah. Okay. Oh, yeah, that's a lot of fun. Definitely, I'll put that's in the show notes. Go there, listeners. Last follow-up questions I had based on what you said before with more, I think about causal inference, because you said that the two most important variable to have when you are thinking about the efficiency of a treatment is intent to treat and randomization. So first, how wrong am I in the summary I just did? And second, and most importantly, why?
And you might substitute for efficiency the word unbiased. You want to have an unbiased assessment of the treatment effect. So that's what the design has a lot to offer. So randomization is going to give you a way to estimate the treatment effect that's unbiased by patient selection, because you're not allowing the doctors to select patients for the treatment where they might select sicker patients for the newer treatment. You're not allowing that.
That's the case where you design.
Yes, and you impose experimental intervention.
Okay, I'm guessing you did something like that for COVID, but we're going to talk about that a bit more at the end of the show. First, I'd like to get back a bit back to your background, because a question I ask all my guests is, do you remember when you first got introduced to Bayesian stats, and why did they stick with you?
First question is, why did it not originally stick with me? So like many graduate programs, the one I went to in North Carolina, Bayes was taught for about 4 hours total. And so it was so minimal, and the professor made it so distasteful. And I think somebody even put an anonymous classified advertisement in the newspaper in the town saying there was a rumor that Professor X was a Bayesian, like it was, he was in the closet and needed to hide somewhere. So Bayes was looked upon with disdain and taught that way, and taught that you need conjugate priors, which means you would only use it if you had a contrived situation that doesn't match the real problem, but it's mathematically solvable. So that was turning me off for years and years and years. And then, of course, the software wasn't there to be able to do it anyway. So we didn't have a way to facilitate it. It wasn't until I started getting to know better the work of David Spiegelhalter, who is one of the world's greatest biostatisticians of all time. He's in the UK and is very involved in statistical education and working with the BBC. And of course, has written amazing, wonderful papers, classic papers. So the way he's a Bayesian, and the way he always attacked a problem was not from philosophy, but from problem solving. And so he got my attention by the problems he was able to solve with Bayes. And at the same time that I got to know David Spiegel's work, especially an amazing classic 1994 paper in the Journal of the Royal Statistical Society, is I was having problems that I was having difficulty solving. And the key problem for me was in a randomized trial when you want to do sequential monitoring and with possible early stopping for a conclusion of efficacy or harm. So I started to study the group sequential monitoring boundary approach, and I found it very complex. And I kept trying to understand it and kept trying to understand all of this business about alpha spending. And then how do you know that you're choosing an alpha spending function that is rational? And I came to understand that there's no real statistical principle that guides the selection of the stopping boundary or the alpha spending function. And then the math is very complex for deriving the stopping boundaries. And then you don't have a p-value anymore when you're done. All you know is that you were within the stopping boundary or not, but there's no way to really calculate a p-value in that setting. And so all of that was really, really turning me off. So the inability to understand group sequential methods is what really drove me totally over to Bayes. And then I saw how Spiegelhalter and others were doing this, and I was very attracted. And I was also working in the same building as Don Barry, who's the biggest Bayesian biostatistician in the US. And I started coming to his office down one floor at Duke University in North Carolina. And he was giving me a lot of mentoring and a lot of good advice about learning Bayes and what Bayes would do for you. And so that's really what got me into it. And one thing that got Don Barry into Bayes also got me into it. He was a frequentist teaching in a great statistics program at University of Minnesota, and he would try to teach confidence intervals to his students, and they could never understand them correctly. He tried for years. They could never give a correct answer to what a confidence interval really means and how do you interpret it. He just woke up one day and said, either I'm a terrible teacher or the concept is defective. So he concluded the concept is defective, which is exactly what I conclude. And so that really helped drive me to Bayes, just like it did for him. The Bayes is so much more straightforward and direct.
Yeah, well, I mean, you're preaching to the choir there, but completely agree. I actually read the other day, I talked about that with Alan Downey in episode 41, but I read the other day an article by E.T. James about the difference between confidence intervals and Bayesian credible intervals. And this article is really great. It's of course a bit old, but I mean, it's like the theory hasn't changed that much around that topic. And the article is just also a delight to read. It's quite fun, actually. So,
and one thing the Bayesians do that is they try to get us not to use credible intervals. You know, credible interval is what you get as a simplification, but you're really talking about a distribution of fuzziness. So how fuzzy is your knowledge about something? It's a whole posterior distribution. And so Bayes really doesn't want you to reduce things to a number or two numbers like a credible interval. We do that only for convenience. But the idea of saying, I'm not going to tell you a point like a mean or a median. I don't want to tell you a point because the data are just looking through the glass that's a smoky glass. You're looking through this haze, and the data gives you kind of a little bit of a view towards the truth. But Bayes invites you to just be totally honest about the complete picture of uncertainty.
Yeah, I love that. And I don't know why, but that reminds me of something I read somewhere. I'm unfortunately unable to remember where, but that was something like that, where when you're a modeler, you basically can see the world, but only through a tiny window. And imagine that you see the forest, you see a part of the forest, but there is fog. And also there is two parts of the forest that you don't see through the window. And so it's not only important to say what you're seeing through the window, but how clear what you're seeing is, and also what it's possible that you don't see at all. That's completely related to what you were just saying. And yeah, so you're definitely in the camp of people who came to Bayesian stats through pragmatic decisions. And just yeah.
It's a little bit ironic because most people are convinced to get into Bayes because of problem solving. That's definitely what got me involved. And the more I'm into Bayes, the more I see the philosophical advantages that nobody wants to hear about. So I talk a lot about philosophy and I create enemies that way, but I can't help myself.
I mean, I completely agree because I'm a bit of the same, but because I'm fascinated also by all the philosophy behind that and the way it allows you to make decisions and also to reason about the world, like not only about statistical models and numbers and figures, but also how to think critically and being able to basically be a critical thinker and when to know when you should update a belief or not. But yeah, that kind of stuff is not really what convinces people who are outside of the Bayesian field. Really, it's often just something very pragmatic and, I need to solve that. I can't solve it with the statistics I learned at the university. Help me. And then you get into Bayes. This is what you did.
And there's one other side of it that's unpopular with some people, which is a lot of the solutions we have to problems that are easy and the ones that are taught in school are not actually solutions to the problem anyway. And so they're a substitute problem that's easier to solve. So they change the question just to have easy math to get a so-called objective answer. So one of the hardest educational tasks that I face almost every week is convincing someone or trying to convince someone that the approach that they've been using for the last 20 years never solved the problem that they think it solved. And the worst example of that is talking to famous people who are brilliant scientists who will say that the p-value is the probability the null hypothesis is wrong. So there's still people that actually believe that, and you just write down the equations to show them it couldn't be more wrong, and they will not understand what you're saying.
Yeah, or, I mean, they probably understand if they are indeed very brilliant, but like it's just something like, cognitive dissonance, your brain really doesn't want to understand that, and because it can also completely undo part of your identity, which is something quite hard. And actually, we talked about that in episode 18 with Daniel Lakens, who is doing a lot of work about the replication crisis and so on. And basically the idea is a bit of the same, because then you're saying, okay, your paper on which you worked for 5 years, actually, the results are not very robust. We can't really replicate that. Doesn't seem to be true. That's good for science on a macro level, but on a micro level, that's hard, because you have to say that to someone that you often know, because science and research are a small world. And so you have all these identity and ego questions that get thrown in the mix and complicate everything even more.
And I think that's incredibly important. And the way that I think about that is people don't need to say that everything they did was wrong and was a failure in order to embrace something that's an improvement over what they were doing. I always say upward and onward. And I don't have to declare my past a total failure. I just want to be doing better each week than I was doing before. And so I've reinvented myself multiple times. I mean, I was anti-Bayesian and I was the first SAS user. So I started using SAS 1969, 68 as the first real SAS user outside of the group that invented SAS. And when I saw the S language, I immediately abandoned SAS in 1991. I've never used it since. So the fact that I had written a lot of SAS procedures, like the first SAS procedures for Cox regression and logistic regression, and I was a devout SAS user. Once I saw something that was more efficient and productive for me as a problem-solving software system, I just immediately jumped to that. And I didn't have to apologize to anyone for my past.
Yeah, exactly. I love that. And that's just a way of, it's related also to something that you learn from a philosophical standpoint when you dig into Bayesian philosophy, is that you shouldn't judge your decisions by their results, but you should judge them by how you got to make that decision at the time with the information you had available at the time, and not afterwards with hindsight bias. So it's as if you were judging yourself right now for being an anti-Bayesian. That's not really the point.
That's well put.
Actually, okay, I love that, but I want to ask you about clinical design now, or clinical trial design. You talked a bit about that at the beginning of the show, but can you tell us maybe why it's useful, and also what's the difference between a Bayesian design and a non-Bayesian one, if there is even a big difference?
Oh, yeah. Well, the design is useful and just all important, because I think everyone knows you can't rescue a bad design with a good analysis very often. So design is how we create efficiency and freedom from bias. And no matter if you're a Bayesian frequentist or a likelihoodist, the design is just all important. I think what's different about Bayesian design, and really likelihood design is similar to Bayes in this way, compared to traditional frequentist design, is that frequentist design tends to be very inflexible. So you tend to not have good ways to handle changes of the design once a study starts. It's very complicated, and one of the complications there is alpha spending. So there's this real preoccupation in the classic frequentist design world to control the type 1 operating characteristic, probability alpha, which most statisticians call that the type 1 error, and I'm very clear always to never call that an error, because it's not the probability of making an error. It's a probability of making an assertion about something if there's no activity of the treatment. And so there's this preoccupation with controlling alpha. So when you're designing a study and you have more than one outcome or more than one assessment time in a longitudinal study, your alpha grows because you have more opportunities for the data to be extreme as you look at more things. And so when you look at how much effort is expended in the design phase of a study around the calculation and preservation of alpha, it is an unbelievable amount of time that it makes people do extensive simulations, and they agonize over what's a primary outcome, what's a secondary outcome, what's a co-primary outcome, co-secondary outcome. Most of that is motivated by alpha spending, not all of it, but most. The idea that you have to control the probability of ever making an assertion of efficacy if the treatment does nothing has created a whole cottage industry of statisticians, but has made every trial much slower in getting off the ground. So Bayes cuts through that, because Bayes says we want to maximize the probability of making the right decision once the data are available. We don't really care about designing a study for what might happen. So we don't want to design a study around the probability that we would ever declare a treatment as effective if it's not effective at all. But we want to design the study around the probability that the treatment actually works, given the best available data at a given point in time. And if you look at those two things, they are as different as night and day. And it just so happens that the probability that something works, given the current best available data, is something that doesn't get modified by the fact that you calculated that probability a few weeks ago. So if you calculated the probability of efficacy as 0.92 8 weeks ago, and now you have new data, the probability is let's say 0.95 now, the 0.92 is gone and forgotten. So the probability of efficacy that used to be the best available probability is no longer the best available, because we have new data that's overridden the old data. So the old data are obsolete. So when something's obsolete, nobody gives it a second thought. it's time to forget it. So you forget the 0.92. The 0.95 will be forgotten if you get new data, and the posterior probability is now 0.93. So the fact that the current probability makes all previous probabilities obsolete means that there is nothing remotely like alpha in play. And the reason is you're calculating probabilities that are forward, they're predictive in nature. When you're playing soccer and you're making a prediction about whether your team is ahead by 2 points is going to go ahead and win, your prediction will be based on how much time is in the game, how fatigued did the players look, and all that. And then the game keeps going on and you keep updating your probability. Well, the probability that was in play 15 minutes ago is not of interest to anyone anymore. The current probability is everything. So once you go into forward probabilities versus backward probabilities, everything changes. And so when you're designing a Bayesian study, if you're using purely Bayesian principles, the design is so much easier. And likewise, if you have multiple questions, Bayes would say that the way you control how careful you are, because you're trying to take a risk by learning more from the study than just answering one question. Does a drug lower blood pressure? Well, I also want to know, does it lower the chance of getting a stroke? So how would you deal with multiple questions in the Bayesian forward probability space? Well, the way that you interpret the evidence for each question is one question does not make you more skeptical about the other question. So that no matter what the data say for a stroke, you can interpret the results for blood pressure. And the skepticism comes from the experts' skepticism about a blood pressure effect. So the skepticism on the blood pressure effect doesn't come from skepticism about stroke. The skepticism about a stroke effect doesn't come from skepticism about a blood pressure effect. So the skepticism comes from the pre-data likelihood of an effect on that endpoint. And then no matter how many endpoints you look at, the skepticism will make the assessment of evidence for that endpoint be less sharp if you are more skeptical and the scientific community is more skeptical about the action of the drug on that one endpoint. And so the way you think about multiplicity, everything is so trivial in the Bayesian world. Once you get past this argument about the prior distribution, you're focusing a lot of arguments into one argument. Everything is so clean and simple after that point. And it makes you able to get studies off the ground much faster than arguing endlessly about co-primary endpoints and alpha spending.
That's well put. And actually, I see how useful that is. And do you have a favorite research paper or experiment on the topic that could maybe help listeners understand concretely how this is used, and we could put that also, of course, in the show notes?
I think the Spiegelhalter, Friedman, and Parmar paper from 1994, this was in JRSS-B, Journal of the Royal Statistical Society, Series B. It's a fabulous paper. And then Spiegelhalter and others wrote a book about Bayesian methods in health evaluation. So that covers both clinical trials and in more observational clinical research. So that book is just a classic book with just a real problem-solving approach. In terms of non-biostatistics, the book by Richard McElreath, Statistical Rethinking, which I think is in its second edition, if I remember correctly.
Yeah.
That book is the most intuitive statistics book I've ever seen. It doesn't really delve into biostat, but general stats. So it's a first book in statistics that uses no frequentist concepts. And if you start with the Bayesian approach, if we could make that the first course that anyone gets, the intuition that book gives is so dramatically beautiful. Just imagine a first book on statistics that covers how to deal with missing data and measurement error, because it fits into the Bayesian modeling paradigm more naturally than it does in the frequentist. And so many other complexities. Here's a first book of statistics that covers how to calculate the probability that model 1 is more likely to be the true model than model 2. It's incredible, that book.
Yeah, I completely agree. And each time I have to integrate measurement error in my models. I'm amazed. This is so great. Or even missing data. Like you just, the answer is so simple each time is, okay, I don't know very much about these data, they have measurement error around them. What should I do? Well, put a distribution around them. It's amazing. These data points, they are missing. What should I do? Put some distribution around them and then let the sampling algorithm do the work for you. It's really amazing. And it's also super intuitive. It's like it makes sense. If your data, for instance, if I go back to political election forecasting, where you have measurement error, is polling. I mean, polls are really, they are data, they are observations, but they're really noisy observations. Well, you can put measurement error around that and integrate all that into your model. And it's super easy to do that in the Bayesian settings. I wouldn't wait to have to do it otherwise.
There's a simpler example of that, which I go into detail in this course I have called BBR, or Biostatistics for Biomedical Research. And it's
which will be in the show notes too.
Yeah, hbiostat.org/BBR. This is the Bayesian Ttest. So if you think about how we usually do a t-test, we're not very honest. So we may look at normality, we may look at equivariance and choose an equivariance t-test versus unequal versus a Wilcoxon test. It just so happens when you do that, your confidence interval at the end is not honest anymore. It's too narrow. So it doesn't reflect the chances you gave for the data to look non-normal or unequal variance. Whereas a Bayesian t-test, you would have parameters for the variance ratio and for the degree of non-normality. The fact that you are being honest that you don't know if the data are normally distributed or if the variances are equal means that let's say you're doing a credible interval, it'll be a little wider than the confidence interval because the confidence interval is a misrepresentation of the analysis. And statisticians make a tremendous error in saying that the confidence interval was computed using a critical value at 0.95. So they say it's a 95% confidence interval, but it's not a 95% confidence interval. It might be an 88% confidence interval because they're too afraid to do the simulation study that calculates the true coverage probability of the confidence interval, and they're calculating the conditional coverage probability, assuming normality and equal variances. And so that creates overconfidence, and that kind of overconfidence is one small part of the reproducibility crisis in science. We need that interval to be wider when you don't know the data are normally distributed.
Completely. So maybe to go back to Bayesian decision making, because it's something you do a lot, and I think you made a pretty good case of explaining why Bayesian statistics are helpful in medical decision making. So now I'm wondering about the current main challenges of the field, because like the frontiers of the research in this field, if you will.
Yeah, there's so many frontiers, it's hard to know where to start. But one of them that relates to decision making is the challenge is that everyone is afraid of decision making. So everyone makes decisions every day. They don't want to be told how to make decisions better. And so if you were to actually do a cost effectiveness analysis or a utility assessment and derived a loss function to find out what is it that people are trying to accomplish, you can improve the decisions by doing formal decision making, and nobody wants to do it because the time it takes to get the utility function is a time they didn't put on their calendar. Like in Bayes, you have all these arguments about the prior distribution. The arguments about the utility function are even worse. So people want to avoid that because the different people have different utilities. Like if you're in a public health field, you're going to have a different utility function than if you're with a pharmaceutical company or with an academic organization or running a hospital. The idea of actually doing decision-making would be a really neat idea if we did it. I don't actually do formal decision-making because I'm not involved in any situation where we have the utility or loss functions actually specified. But I like to act in a way that would feed into the optimum decision. And so the optimum decision involves the consequences of all the possible decisions you might make. And you integrate that with the Bayesian posterior distribution about the parameter involving that decision, such as does the drug work. And you get this sort of averaging process to get the expected utility of various decisions, and you choose a decision that has the best utility. So the fact that we're so afraid of doing that is really telling, because we tend to design studies that have an alpha of 0.05 and a beta of 0.2. So we're saying to the world that a type 1 probability, a type 1 so-called error, is 4 times more important than a false negative. We have not done the right decision to really say, how do we want to weigh missing a treatment that works versus blessing a treatment that doesn't work? So we're never willing to say, what trade-offs are there? And what if the treatment is cheap and it has very few side effects and it has a probability of 0.86 of working? Maybe we should be using that treatment. I think just the absence of decision-making is holding us back, but at least we should approximate optimum decisions using Bayesian posterior distributions that are what the key element besides the utility function. In terms of other frontiers, we have a lot of issues with model specification, and I think if we spent more time specifying models wisely, such as the measurement error model you mentioned, where you're incorporating the fuzziness in the data, and there's many other models where we assume a patient has a certain diagnosis, but there's uncertainty in the diagnosis. And so there's a lot of uncertainty in how you handle longitudinal data. What is the most flexible and most likely to fit longitudinal model you can use for a certain type of measurement, outcome measure? In the frequentist world, there are a lot of methods that are used every day that are not good enough. So we're using logistic regression all the time, and logistic regression is a wonderful tool, but the confidence intervals we're computing from it are not very accurate. And so people are not questioning things that are done every day in terms of the accuracy of the normal approximations that we commonly make. And Bayes just says, well, forget all that. We're not going to do anything that assumes the log likelihood function is quadratic or the estimators have a normal distribution. We're not going to assume that. So nothing we do is going to depend on that. Whereas in the frequentist world, much of what we do depends on normality approximations, normal approximations. So I think model specification needs to get smarter and more flexible. So one of the examples I've already touched on, you have a treatment that might reduce symptoms or it might reduce mortality. We need to be really smart in how we allow the treatment to affect those two outcomes differently, but not so differently that you need to have 10 times the sample size to have enough deaths observed. So we need to borrow information between deaths and non-fatal outcomes. We need to learn how to borrow the right amount of information. So this idea of borrowing information, which is well worked out in terms of using historical data, is not well worked out in terms of borrowing information across different parameters in a model. It's just like when you're going to allow the data to be non-normal, how non-normal are you going to allow it to be? So what should be your prior distribution on the non-normality parameters? That needs to be worked out better. So there's a lot of modeling things that we need to do better. A lot of work still to be done in semi-parametric models, especially for more complex distributions and models and longitudinal data. And then there's the high-dimensional world of omics and genetics and microbiome, where we're still working out a lot of solutions. And Bayes has been really on the forefront of a lot of the work, a lot of the best work in the high-dimensional feature space setting. So I think there's so many frontiers out there. Missing data is always a huge challenge. And we need to do better in terms of missing data. Bayes has a lot to offer. You've already mentioned handling missing data with formal modeling in Bayes. Bayes can also do multiple imputation using posterior stacking, and that works better than frequentist multiple imputation. You're actually using standard multiple imputation for both Bayesian and frequentist, but the way Bayes does the inference after you've done the imputation is more accurate because it doesn't assume normality and it doesn't need to use Rubin's rule for how you combine the multiple imputations. It just stacks all the posterior distributions into one giant posterior distribution that has heavier tails. And the tails are heavier because imputing missing data involves the creation of a certain amount of extra volatility. And the posterior stacking does that in a way that's significantly better and easier than using Rubin's rule and trying to come up with degrees of freedom in a t-distribution that reflect the non-normality after you've done multiple imputation.
Yeah, I think they talk about multiple imputation for missing data in regression and other stories. The book by Andrew Gellman, Aki Vettari, and Jennifer Harrell.
I just bought that book and I'm looking forward to getting into it.
Yeah, it's really great book. And I do seem to remember they talk about that in the chapter about missing data. And I refer listeners to episode 20, special episode we did with the 3 authors, and we go through some of the things you learn when reading this book. So
wonderful.
Yeah, if you want to have kind of a audiobook bonus while reading it. And that's funny to me because like often the classic rebuttal of Bayesian statistics is, yeah, but you need those priors. And so basically you can fudge your analysis to get exactly the results that you want. That's the caricature. So it's very subjective, whereas frequentist statistics are much more objective. They don't have assumptions, basically. And that's funny to me because you're saying the contrary. You're saying, but no, you always have this normality assumption that often falls apart. And then in these cases, you're in really, really big trouble because you're assuming something that's basically non-existent and you don't even remember and realize that you're making this assumption, and then you're overconfident in your results.
You couldn't say it better. And that COVID-19 Project website that we've created, the first link on there is our comprehensive clinical trial design and analysis document for COVID therapeutic studies, and it goes into details about comparison of Bayesian and frequentist. So it has a side-by-side table that has what are the differences and similarities. And it goes into what is subjective about the frequentist approach. And I think it makes the case that the frequentist approach is more subjective than the Bayesian approach, not less. And then we have a mind map of the frequentist paradigm, a flow diagram, and we have a mind map of the Bayesian paradigm in that same document. So that's really trying to help people with the understanding the differences in the two paradigms. But it really does spend some effort trying to address this point, which I think is so wrong when people say Bayes is more subjective than frequentist. It really is really not the case. And when you get into how arbitrary you choose a multiplicity adjustment in the frequentist world, I rest my case.
Actually, you can talk a bit more about this COVID-19 project if you want now. I think it's a good case. We mentioned it at the beginning of the show, but if you want to add something about that, feel free to do it now.
We thought this was a great place to push Bayes even harder because things happen so fast with COVID. We need to make rapid decisions about releasing treatments onto the public because of so many complications of COVID. And Bayes is really made for this sort of flexible, quick learning situation. And then, so we spend a lot of time motivating that, urging people to use it. Some of the people that have taken it to heart the best are a series of COVID-19 trials based in Paris, where I'm on the data safety monitoring board for that group, and they have really gone with Bayes, and I'm really glad. Other people in the U.S. have been more hesitant, and my greatest disappointment of the past year is to learn that in an emergency situation where you need faster answers than before, tradition still trumps efficiency. So we have found that we're very threatening to a lot of people that are dedicated to the very rigid kind of clinical trial design that's usually done with the frequentist paradigm. But the other way that Bayes helps is in the modeling and allowing you to do more flexible modeling without making large sample approximations. So coupled with some of the stand code that we've developed and our package that uses that stand code, the ability to make for more flexible modeling that allows you to make statements that you would never dream of making in the frequentist world because the Bayesian modeling is so flexible. So the example that I've mentioned earlier today is the Bayesian statement would be the probability is 0.8 that the treatment changes mortality in a way different than it changes symptoms. Just think of that posterior probability. What does that mean to a clinician, and how useful is that compared to somebody looking at whether the p-value for one of those is greater than 0.05 and is less than 0.05 in the other? So here we get a direct posterior probability for the dissimilarity of effects of a treatment on two different outcomes. And that's just an example of what Bayesian modeling can do for you. So that website, it has everything we've worked on with lots of examples, lots of R code and notebooks showing different analyses. And I just urge people to look at it because there's a lot of stuff there and a lot to do with longitudinal Markov models, which is what we think is the most flexible and appropriate way to model a lot of the sort of time series and longitudinal data we're seeing in clinical trials today.
Definitely worth checking that out. And I mean, this is really fascinating. Now we're getting short on time, so I'd like to ask you two questions before the two final traditional questions. I like to focus also on failures, like to not get, fall into the trap of survivorship bias. So instead of thinking about the modeling successes, do you have in mind a big modeling mistake you made one day, and how did you realize it and solve it in the end?
Although I've made so many mistakes, I've made them all, and I just try to not make the same mistake over and over, but I've made a lot of mistakes at least once. So the one that just immediately comes to mind is when I was in graduate school, we were taught that you could select models on the basis of p-values. And that was, people didn't know any better then, but that's what I was taught. And so we were basically taught if you didn't get a singular matrix, you could fit anything. And you could play with the model and you could try different variables. And so you could do stepwise regression. So stepwise regression was taught. Many graduate programs are still teaching it. It's hard to believe, they should be banished off the face of the earth. So I was using stepwise regression. Then I started implementing SAS procedures to do Cox and logistic regression, as I mentioned. And I put stepwise regression in those procedures because everybody else did. I started working with a physician oncologist, Tom Reichert, who was also had a PhD in physical chemistry. This is a bright guy who was running a pattern recognition company using machine learning back in, like 1980. And he was predicting weather and nuclear rod failure in nuclear power plants. And he said, you really need to start holding back data to see if your models are validating. And I was already getting flack because we would update our follow-up with more patient years of follow-up, and a variable that was selected by p-values was no longer significant, even though the sample size was bigger. So the cardiologists I was working with were already concerned that we were changing our minds too often, and what we were doing was unstable. So Tom told me, you need to start holding back data and doing validation because you'll be surprised that a lot of the models you're developing are not as good as you think they are. And I told him, I'm using things like X prime X inverse, X prime Y, and I'm using regression theory. It's unbiased. It has to work. He said, start holding back data. You'll learn a different lesson. I said, I don't need to. I'm using my theory. And he said, look, I really think you need to hold back data. So after he pushed me 3 times, I started doing it. The models were falling apart. I was totally embarrassed. Everything he said was exactly right. And his getting me for the first time to get involved in model validation, it told me that I was doing things that were highly unstable and volatile and not reproducible. That changed everything I was doing. And so that's when we started to get into unsupervised learning or data reduction so that we reduced the dimensionality of the covariate space so that we would get more stable. And then we got into Bootstrap and Bootstrap model validation to learn about the overfitting before you waited for a new data set. So that was a game changer. And I was totally embarrassed that what I had learned in school was not correct. And I wasn't going to keep making that same mistake. And so I've been trying to teach everyone that I could get within earshot of that, Stepwise regression is really a way of turning your thought process over to a computer. And we can do a lot better than that. It just takes a little bit of work.
I love that. I love that story. There is a lot of things to unpack. But yeah, in the end, you learned a lot from this mistake.
I didn't feel like I needed to declare everything I did a failure in order to go from there. I just wanted to do better, and I don't care if it required a change. Just like I've changed software dramatically and just totally abandoned software that I was dedicated to. I don't think that's a bad thing. I think I just want to be doing better.
Very great mindset. I love that. Let's say that I'm a beginner in biostats, or that I'm thinking about going into studying biostats, and I would like to emulate the work you do. Which skills should I develop, and which mistake should I avoid, or maybe I should make to learn best?
That's a great question about which mistakes are most helpful. I need to think about that for a future day, because that's a great question. But in terms of the other parts of your question, there's several skills. Of course, a central skill is curiosity, or it's not a skill, it's a love that you have. You're just curious about learning and learning different things. But in terms of more concrete skills, two that mean everything to me is, one is being able to program efficiently using good programming practices. So the better you are programming efficiently and in a way that you can keep reusing your code and stealing from yourself. I have code I'm using now that was written in 1978. And that leads into the ability to do simulations efficiently. So if you're able to do simulations efficiently that reflects some reality, the way you're simulating data, the skill of doing simulations, it changes everything, because you learn quickly what doesn't work that you were going to teach someone else. Before it's too late, you learn it doesn't work, or before you use it in a big clinical trial. The ability to run and design and code simulations is key. And then another skill is reading. So you learn which 15 journals you need to read. There's usually more than 10 journals you need to look at. And I don't mean read them, but I mean read the abstracts. And you have a news reader you set up that's always alerting you to new articles in the journals that you're following. And so reading is key, because that's how you keep up with the solutions that people are coming up with. And which journals do you read? I know certain journals have more problem-solving papers than others. Some journals are really all about publishing PhD dissertations that was required to be published for the person to get their PhD. Those are not tending to be as useful as the papers I see in, say, statistics and medicine. So reading is really key. And then I swore I would never use Twitter, but once I started using Twitter, I learned so much from other people on Twitter. It's almost frightening. I cannot believe how much I'm learning. Somebody will point out a tweet to something I never would have thought of in some journal or website I never heard of, or they would say, we have a preprint and you might be interested in this about this way of handling missing data or whatever. And so I get all these alerts from people that I follow that alert me to some new resource. It could be new software, it could be a new article, a preprint, or a new course that somebody developed, or a new online presentation. And that has really been an eye-opener for me. So I've moved more into the modern social media setting that I never thought I would do. I'll still never, ever use Facebook as a matter of principle, but Twitter is another matter.
I learned so much on Twitter, actually, too. And I think that's one of the ways I found out about your work and and what you do, and all the Bayesian work you do. So I mean, that's great. And thanks for all these great advice, very concrete advice. I love that. That's great. I have to ask this question more often.
And just one other general one is take everything with a grain of salt. If you believe everything your professor said in graduate school, you're in trouble. A healthy skepticism is all important. That's how you get rid of things that don't work and you learn to use things that work better. So I just be skeptical about most everything you encounter, especially your professors.
But methodical skepticism, I guess. Having a good method to decide whether you should be skeptical or not. And that's where we tie that up with Bayes' theorem.
Has a lot to do with it.
Exactly. Okay, Frank, before letting you go, I'm going to ask you the two questions I ask every guest at the end of the show. So first one, if you had unlimited time and resources, which problem would you try to solve?
I would try to solve, in machine learning, people try to create algorithms that can learn from a wide variety of situations. I do that in modeling, and I want to do it better in modeling. So I want to have a model that learns more about the distributions the data are coming from and is more flexible in the same spirit as semi-parametric models, but take that a step further. I want to have models that are smarter in dealing with interactions. So interactions is one of our greatest challenges. We basically have to pre-specify interactions in the regression modeling world. Machine learning doesn't, but they require huge sample sizes as a result. So something in between those two in dealing with non-additivity and interactions. So in general, I would like to have a more general way to pre-specify a modeling procedure that would handle a wider variety of problems than we're currently able to handle.
I get that. Second question. If you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be?
First of all, my role model is a fictional person. My role model as a statistician is Sherlock Holmes. I see statisticians as detectives, but in terms of scientists, the four names that come to mind for me is Bayes would be one. Because Bayes didn't talk to anyone about what he was doing hardly while he was alive. But the other ones would be Charles Darwin, Isaac Newton, and James Clerk Maxwell. So James Clerk Maxwell was a physicist whose work set the stage for Einstein and was an unbelievable brain and really kind of underappreciated. But I read a biography of him that is one of the most stunning lifetime accomplishments by anyone. And there's so many other scientists that would be great to spend time with, but those are just some that I think of immediately.
So many people. That's the beauty of this question. Frank, thanks a lot. This was a fascinating dive into biostatistics and how helpful Bayesian inference is there and even is in general. Thank you for spreading the Bayesian world and for all the important work that you're doing, especially in the past year. You really are passionate about what you do, and that really shows. I'm sure listeners will hear it as well. As usual, I put resources and a link to your website in the show notes for those who want to dig deeper. Thank you again, Frank, for taking the time and being on this show.
Yes.
Yeah, this really was a fascinating conversation. I love that. Best way to spend a Thursday evening. So thank you and take care.
And Alex, I can't thank you enough for the invitation and for making this so much fun. Totally enjoyed it. See ya.
This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and subscribe to the show on your favorite podcatcher or on Podchaser, and visit learnbayestats.com for more resources based on today's topics, as well as access to more episodes that will help you reach true Bayesian state of mind. That's learnbayestats.com. Our theme music is Good Bayesian by Baba Brinkman with MC Lars and Megaran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbayestats. Thanks so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.